And we will now go on with the agenda. And our next speaker is Dr. Ronald Müller, CEO of the Vision Markets company, who will speak on behalf of Reuven Weintraub, CTO and founder of Gidel. And Mr. Müller will speak about overcoming the bandwidth limitations of vision on the edge. So, yeah. Mr. Müller, we're looking forward to your presentation. The stage is yours.
Thank you, thank you. Yeah, welcome everyone. And thank you, Carsten, for ruining the motivation of my talk, because there is one way to overcome bandwidth limitations, with this reducing the bandwidth on the sensor side. What I will be talking about is reducing the bandwidth right after the sensor. First of all, maybe some words about Gidel. Gidel is a technology leader in FPGAs. So Reuven Weintraub, I think, is one of the renowned kind of reference people in the industry when it comes to FPGA know-how. And he has founded Gidel more than 25 years ago. And now Gidel today is offering hardware platform and programming tools for FPGA implementations and FPGA solutions. So you can see like hardware solutions, IP cores with corresponding algorithms on it, as well as the development of full solutions in a customized way. The typical application areas where Gidel is in is data centers and high-performance computing, HPC, imaging and vision, and also many other types of innovation. Right, so let's start relatively basic. What's vision on the edge? And I hope we can agree that in a typical scenario, we have a camera, we have an edge computer, or an embedded computer that is sitting next to the camera, and we have a processing or storage in the cloud, and we have then some machine control. And also today, I heard the feedback from customers that they say, it's not enough for us anymore to have one output of a camera with 1 GHz channel just to connect it to a PLC or something. We want a second output of the camera with another GHz channel to transmit the images to a cloud server. So I hope everyone can agree so far with this setup. Now, here is the challenge. We do have a need and a rush basically in the industry for more pixels and more frame rate. Yeah? So the people want a higher spatial resolution and a higher time resolution. And accordingly, you can see here a number of image sensors. Oh, sorry. Yeah, so the image sensors are these brown dots. And the lines are representing the typical interfaces that are common in our industry. Yeah, so on this Xeon line is 100 GHz. PCI Express Gen 3 is the blue line. Coax Express version 2 with 4 lanes is the red line, and so on. And you see, when an image sensor is above a certain line, this interface is not sufficient anymore to transmit all the data that this image sensor could provide. And as you see here, you already have a number of sensors that are way faster than 10 GHz, are way faster than Coax Express version 1, and are even faster than the 100 GHz interface, which is currently known as kind of the maximum that is available in the market. So that means there are tremendous advancement on this image sensor level with 10,000s of frames, hundreds and more megapixels, and correspondingly bandwidths that are way above 150 gigabytes per second, or gigabits per second, sorry. So we do have some advancements on the interfaces. We are getting faster and faster. The innovations are coming up also, as we see here on the show. But still, they are, even with link aggregation, they are hardly able to keep up with the pace that the sensor development is providing. And finally, we do have a real issue on the level of the PC performance. So the performance of GPUs and CPUs are lacking behind the advancements in the other areas. That means if we have such a setup with this really, really high-speed sensors with high resolution, we have a number of bottlenecks. One being the camera interface, as we already discussed. Then the interface, the bridge to the GPU and CPU, the load of the CPU, so the processing power of the CPU, and finally, and obviously, the internet connection to the cloud, which is reaching like 1 GE at the best case, usually. Now, things get worse, obviously, if we have multiple cameras. So here, again, imagine you have multiple 10 GE cameras, multiple coax express or even 100 GE cameras in a row. So that means you're getting like, in the case of 100 GE, you're getting like 96 gigabits per second times n, times the number of cameras. On the other side, however, you only have, in most cases, PCIe Gen 3, which means you just have 48 gigabytes per second interface from the image acquisition to the PC, and obviously this is one of their most crucial bottlenecks here. Now, the goal is, and the one approach to the solution here is to put a frame grabber type of device between those multiple cameras and the CPU architecture. And this frame grabber then, or this image acquisition device, can do compression as well as a pre-processing. So for example, just extracting certain regions of interest from the image to reduce the total data bandwidth. So in this image acquisition, you have usually an FPGA, and it's most recommendable to have an FPGA. And you better have a good amount of memory with a very fast interface between the FPGA and the memory. Now, let's say like some requirements on the frame grabbers has come out from such solution scenarios. So you want to have a high bandwidth interface to the camera, correct? You want interfaces to multiple cameras. You want to, as usual, as you want to do with frame grabbers, you need to have a very high time synchronization and customizable I/Os to control peripheral elements and actors on your shop floor environment. In the processing, you want to have it real time, in parallel, multiple, even 100 gigabits per second. That's what you are looking for. And this all should be in low latency with a large DRAM so that you can compute complex algorithms. So you need many gigabytes per second of memory access bandwidth. And then, real-time compression can be a good approach to this, as well as ROI selection. Now, if you put yourself in the shoes of a system developer, the ease of development is also key. So an open FPGA that says I have some specific IP that I want to put on the frame grabber, that is something that you would like to allow. And also, if you have little FPGA expertise, so that should be easy to integrate. For example, by an integrated development environment for FPGA implementations. Fast algorithms should be processed there, off-the-shelf IP cores, so that it should be flexible and easy to use. And then finally, on the system integration side, in the best case, you get a PCI Gen 3 times 8 or times 16 for the maximum performance that is available, like off-the-shelf today. A small form factor with passive cooling. So that's the wish list, the Christmas wish list of our customers. Right, so what if you had a solution where you can combine the grabber and the PC all in one? For example, with a high-speed camera interfaces, with a built-in frame grabber and an FPGA pre-processing inside. For example, with an NVIDIA Jetson to allow for AI or also fast GPU-based processing. A good and fast PCIe interface, easy programming, and then a 1 GE output to the cloud or to the shop floor equipment, or even a 5G output with wireless connection. So that is also an opportunity. And Gidel has come up with a solution, which you see here. This is called the Fantovision. Here you have in one PC the frame grabber with the very high performance FPGA inside, and you have an NVIDIA Jetson, and that is, so to say, a unique standalone solution where you can reduce bandwidth heavily and do the computation of very, very large amounts of data. Now, a little bit of summary here and some application example. So you have the highest bandwidth in the camera. You're reducing it further through the frame grabber. You put it then on the host GPU or CPU, and then obviously you have shrinked it down and melted it down so that it can be transferred to the cloud. So one example of this, for example, could be in traffic, but there are tons of others, as you know, in high performance panel inspection and such type of things where you need high resolution, high speed. So you imagine you have multiple cameras capturing high resolution images. You are extracting the ROI, in this case the car or even the number plate. On the GPU, you can download the algorithms to do the number plate recognition. And finally, you only transmit the number plate or the recognized number plate to the cloud, which does not require a lot of bandwidth at the end. So this is what can be done, for example, with such solutions from Gidel. Generally, there are off-the-shelf products as well as custom solutions, all very well applicable for gigapixel processing, as we call it. So when you have multiple gigapixels per second from a single sensor or from multiple cameras, Gidel has a wide variety of solutions that can do the job and make you enable very new solutions for your applications. Thank you very much.
Okay, Mr. Müller, thank you very much for the very nice presentation. And actually, that was a brilliant presentation, and we must remember that Mr. Müller held this presentation on behalf. So, great job. Yeah.
Thank you.
That can be sometimes a little bit harder than having.
It is challenging, but no, it's
so
it was doable.
Great job. Thank you very much. And actually, you showed a very interesting solution during your presentation. Because at the beginning of this session, I was asking, are new solutions, will they be a combination of FPGA and GPU? And that is actually exactly that, what you've showed in your presentation.
Yeah.
So very promising from my personal point of view. And we will now go on to the question and answer part, and just a general recommendation. On the upper left of every table, there's a QR code. You can scan it, you can log into the conference system, and then ask your question via the online platform. So keep that in mind also for further sessions here at the Industrial Vision Talks. And a question from the audience, can you say a little bit about, because you brilliantly explained the whole hardware and the processing. Can you say about the sensors which can be combined, and with what kind of camera sensors or camera devices that is the most efficient?
Right, okay. Well, the sensors basically depend, it can be any sensor, right?
Yeah.
So the interface of this edge computer as well as the frame grabbers of Gidel are standard compliant. Yeah, so we have Geeky Vision standard. We have they have Coax Express and so on. So we can work with almost any camera. Yeah, that's on the market. Now, the way it's most efficient, obviously, if you have one camera that is creating and providing a large stream in one, this creates the minimal overhead. Yeah, because we have no synchronization of frames and that kind of stuff. So that makes it the easiest. On the other hand, for example, if you have a number of cameras with a relatively small resolution, all these data streams can be processed in parallel inside the FPGA, And then you can also really maximize the utilization, so to say, of the processing power that is integrated in the device.
Okay, okay. Thank you for the explanation. Okay.
Thank you.
Thanks again.
Okay. Thank you.